Okay, welcome to the afternoon session. The first speaker is Anuj Dawar from Cambridge. He's done a lot of work relating logic and complexity. And for this talk, we will have some symmetries in algebraic circuits, and we will see whether that helps or not.
Okay. Thank you very much. First of all, thank you to the organizers for inviting me to give a long talk on this subject. I think Shrikant specifically asked me to make this an overview talk. So a lot of what I say here is not new stuff, background to stuff I've been working on for a few years. So some of you will have heard me talk about this before, but I think for a lot of you, I'm hoping this will be new stuff. I have not, this is my first time attending WACT, and I'm very excited to see such a buzzing community and excited to share this with you. Okay, so I will start by returning to Avi's non-identical grids, the determinant and the permanent. So this is going to be the motivating sort of point of my talk. So we know key aim of algebraic complexity, and Avi exposed this very well yesterday, is to account for the apparent difference in complexity between these two polynomials. We know that the determinant admits polynomial size circuits. We would like to show that the permanent doesn't. And if you restrict the circuit model, we have provable lower bounds, right? We don't know how to prove lower bounds for general circuits, but for suitable restrictions, again, Avi mentioned a whole host in the beginning. Monotone, multilinear, bounded depth, we can get super polynomial lower bounds. But in all these cases, we have super polynomial lower bounds both for the determinant and the permanent, which usually people understand as saying it shows the weakness of the model rather than the difficulty of the permanent necessarily. So one thing, I mean, symmetric circuits give us one way of showing a separation. So a circuit model in which you can prove an exponential gap between the determinant and the permanent. And this is what I want to explain to you in the sort of first half of this talk. This means that for a suitably chosen symmetry requirement, and I'll explain this, what I mean by this, we have polynomial size circuits for the determinant, but provably, unconditionally, none for the permanent. So what I'm going to do in this talk, first of all, I will tell you what this symmetry restriction is. Again, Avi said that the permanent and the determinant are characterized by their symmetries, right, as polynomials. But I'll be looking at very particular kinds of permutation symmetries, which I will explain on the next slide. I'll give you an overview of the results we have on the complexity of the determinant and the permanent with respect to these permutation symmetries. And then I want to do a bit of a dive into the proof methods, because I think that's what's novel here. The proof methods involved in proving the lower bounds, right, particularly. So we have several lower bound results. I will pick one, the earliest one we had, and I will explore that. I mean, I can't give you a full drawn-out proof, but I hope to give you a flavor of the methods involved. And briefly, maybe in the last 5-10 minutes, say something about some new work. Okay, so as I said, we're talking about permutation symmetries. So fix a field K, a set of variables x, and we have a polynomial in the polynomial ring Kx, and consider a group of permutations on this set of variables. Okay, so gamma is just a subgroup of sim x. By sim x, I mean the group of all permutations of x. More generally, I will talk about a group with an action on x, you can, I mean, these viewpoints are mostly interchangeable. The reason for this is slightly pedantic. I mean, I will often have a description of gamma which is different, and I will describe it by an action of x. You'll see what I mean. So, for a permutation on the variables, for permutation pi, I write p pi to denote the polynomial you get by replacing all occurrences of a variable x in p by pi of x. Okay, so we have a permutation of the variables. It induces a permutation action on the space of polynomials, and that's how I denote it. So any polynomial has an invariance group, which is some group of sim x, namely those permutations which don't change the polynomial at all, right? So those permutations for which p pi is equal to p. We say that the polynomial is gamma invariant, right? Remember, gamma is a subgroup if basically gamma is contained in the invariance group. In other words, any permutation in gamma doesn't change the polynomial. Okay, so that's what I mean by permutation symmetries. We're just looking at permutations of the variables and the action they induce on polynomials. Okay. Examples, I mean, classic thing, take the elementary symmetric polynomials, right? So for each natural number n and degree d less than n, we can form the elementary symmetric polynomial of degree d on the variables x1 through xn. It's the sum over all subsets of size d of the degree d monomial obtained by multiplying xi for I and s. This is, as we all know, it's gamma invariant, where gamma is the full symmetric group, right? All permutations fix this polynomial. And here again, I'm being pedantic. Gamma is sim n, and the action on the set x is given by acting on permuting the indices, right? So it's just okay, but you see what I mean. And we know that the elementary symmetric polynomials form a basis for all symmetric polynomials. So we have a good characterization of the space of sim n invariant polynomials, where now sim n is acting on the set x1 through xn. Okay. What about the polynomials we're interested in, right? So the typical polynomials we're interested in are the inputs, or the variables, are entries of a matrix. So in other words, we have a set of variables and they are indexed by pairs ij, where I ranges from 1 through m, j ranges from 1 through m for an m by n matrix. Again, the motivating ones was determinant and permanent. Typically, we're interested in square matrices, so m will be equal to n. But I will say something about the more general case right at the end. So let me just take you through 3 examples: determinant, permanent, and the trace. Right. So the trace is simply the sum of the diagonal entries of the matrix. Now, that's our set of variables x. So if you look at the full symmetric group on x, it's basically sim n times n, right? That would be the full permutation group of all the variables. Of course, none of these polynomials is invariant under that group, right? You can't permute all the entries of the matrix. But what can we say? Well, look at the action of sim n, just sim n, given by taking the variable xij to x pi I pi j. Okay, so pi takes it. In other words, apply permutation pi to the rows and the same permutation pi to the columns. And actually all 3 of these polynomials, the determinant, the permanent, and the trace, are invariant under this action. Okay. So call that simultaneous row and column permutations. For brevity, I will call this square symmetric. The square symmetric action. I'll say these polynomials are square symmetric, and we'll talk about square symmetric circuits as well in a minute. Okay. So, this is kind of the basic motivating example where we have the full permutation group on the set of variables is much too rich. So we're looking at what is effectively a small subgroup, there's still the symmetric group on n, for which these polynomials are invariant. In fact, if you look at the permanent, you can apply any permutation to the rows and any permutation to the columns. They don't have to be the same permutation. You don't change the permanent. Okay? So I will call this, so we have an action of the direct product of sim with itself, where the element sigma pi applied to xij takes it to x sigma pi j, right? And the permanent is invariant under this action. The determinant is not, right? The trace certainly isn't. So we say that the permanent is matrix symmetric. This is my terminology, right? I'll call this matrix symmetry. So neither the trace nor the determinant are matrix symmetric. In this sense, you can ask, what is the permutation invariance group of the determinant, right? Here it is, okay? So this is, take this thing in brackets is a subgroup of this direct product of index 2, namely consisting of those pairs, sigma pi, where sigma and pi have the same sign. And I'll take the semi-direct product with Z2, that's for the transpose, because you can transpose the matrix, and that also doesn't change the determinant. Okay? So that's the permutation symmetry group of the determinant. In particular, it contains within it this subgroup alt n times alt n. So the direct product of the alternating group on n elements with itself. So in other words, I can apply any even permutation to the rows and any even permutation to the columns. That doesn't change the determinant of the matrix. Okay. Right. And now this takes us to symmetric circuits. So for me, an algebraic circuit over a field K is given as a directed acyclic graph where inputs, that is nodes of n degree 0, are labeled by either constants from the field K or by variables x. Internal gates are labeled by plus or times, and there is a designated output gate. Okay? Given such a circuit, an automorphism is just a permutation of the nodes of this directed acyclic graph, which preserves the structure. In other words, it preserves edges. Whenever there is an edge from A to B, there should be, the automorphism should take, pi should take an edge pi A, pi B, and it preserves the labels where the label is a constant or addition and multiplication. So the automorphism must take an addition gate to an addition gate, multiplication to a multiplication gate, and the value of the constants must be fixed. But of course, it can move variables. That's the key point. And then we say, given a permutation of the variables, okay, more generally given a group of permutations of the variables, we say that the circuit is gamma symmetric if for every permutation pi, applying it to the variables, you can extend it to an automorphism of the whole circuit. So in other words, you have a permutation of the variables, you can extend the action to the whole gates of the circuit and giving an automorphism. Now,
so what is preserves the edge relation?
Preserves the edge relation means when you have an edge, its image under the permutation is also an edge. Okay, that's what I mean by preserves the edge relation. So, because I defined it as a directed acyclic graph, it's a collection of nodes and edges. The automorphism is given as a permutation of the nodes, but then it must map edges to edges. Okay. So, clearly, if you have a circuit which is gamma symmetric, then the polynomial it computes is gamma invariant, right? Because that's sort of immediate. The converse is obviously is not true, and I mean here's a kind of trivial example. Take the simple polynomial, which is simply the product of n variables, I can compute it with a single multiplication gate with n inputs. I can also compute it with binary multiplication gates by taking a complete binary tree. I think, well, complete. Taking a binary tree, be complete if n is the power of 2. The one on the left, your left, is symmetric under the full symmetric group on n. The one on the right is not, right? There are permutations of the variables which don't extend to automorphisms of this tree, right? For instance, just swap x1 and x3, right? That's a permutation that cannot be extended to an automorphism of the right-hand side. One, I mean, the automorphism group of this tree is a very interesting group in its own right. You can ask Ben about it if you want to know more. But anyway, one takeaway from this example is Fanon matters, right? So, I mean, I know it's standard in algebraic circuits to say we can, as far as polynomial size circuits are concerned, we can restrict ourselves to Fanon too. I can't make that move, right? Because to restrict your Fanon, you have to break symmetries, right? So since we want to be as permissive as possible, right, we will allow our, we will always have unbounded Fanon gates. Okay. So now we know what symmetric circuits are. What can we say about the determinant, right? So the determinant, remember, we know that we have polynomial size circuits in general. If I take the defining identity, right, this is the definition of the determinant, and I turn it into a circuit of depth 2, right, as a sum of signed product gates. That is certainly alt-n by alt-n symmetric. Apply any even permutation to the rows and the columns. You can permute the product gates and get an automorphism of the circuit. Of course, it's huge. It's of size n factorial. Now, we know that there are, of course, polynomial size circuits for the determinant. Again, Avi told us about this yesterday. You take Gaussian elimination, he says, of course, that involves division. You need to massage it a little bit, but you can get cubic size circuits for the determinant. But they're generally not symmetric, certainly not this rich group of symmetries. Okay? In particular, in Gaussian elimination or similar, you have a choice of pivot. Okay, so in other words, you choose at any stage a row which you're going to pivot. That's a symmetry breaking operation. You're treating one row differently from the others, right? So that's a symmetry breaking operation. In principle, you could try all rows in parallel, right? Because you know it's not going to make a difference. And you can get a symmetric circuit that way, but it'll be of exponential size, right? These choices cascade, and it becomes exponential. Okay. But there is a way of getting some symmetry in a computation of the determinant. A useful way is what are called the various identities, which is a method for computing all the coefficients of the characteristic polynomial. And the point is you can derive these coefficients from the traces of the powers of the matrix X. Okay? So if you can compute the trace of x squared, and so on, up to the nth power, right? From these, you can just compute directly the coefficients of the characteristic polynomial. In fact, here's the recurrence. Cn is 1, and then you recurse for decreasing values, decreasing values of that index. Sorry.
Yeah.
Okay. For decreasing values of the index, so Cn minus m is minus 1 over m, and you sum, the previously computed coefficients times trace of x to the base. Main point here is each of these values can be easily expressed as a symmetric, square symmetric. What I mean is invariant under simultaneous row and column permutations. Same permutation applied to the rows and the columns. And that's because that doesn't change the trace. And you do repeated matrix multiplication to get the powers of x. And matrix multiplication is also invariant, standard method under applying the same permutation to the rows and the columns. So all of those can be computed. And then this expression, once you have circuits for those, this expression doesn't involve breaking any symmetries either. So we get a square symmetric, so sim and symmetric circuit for the determinant, and it's polynomial size. Okay? I wrote characteristic 0, and that's mainly because of this 1 over m you need over here, but this can be massaged, and you can get versions that work in positive characteristic, arbitrary characteristic as well.
Do you get n cubed here?
No, n to the 4th is the best I know. But I mean, I haven't tried to optimize it. Yeah.
What is m here? Because I think you said that we have square matrices.
No, sorry. This is a recursion. We're calculating the coefficients of the characteristic polynomial recursively on m, or inductively on m. Start with m equals 0, and then for increasing value of m, I have this expression, and notice it's given in terms of the previous values, right? And so the determinant you get at the end when m is equal to n. Okay. So for the permanent, if I take the defining identity, right, the sum of the permutation monomials, it is what I call matrix symmetric. In other words, it's invariant under arbitrary row and column permutations, and it's of size, depth to order and size n factorial, as we know. We can do better than n factorial. We know that by Reiser's formula, right? This gives us size n squared times 2 to the n. But this is still matrix symmetric. So this is a symmetric circuit. There's a depth 3 circuit, which is still invariant under row and column permutations, right? So it gives us a matrix symmetric circuit of size n squared over times 2 to the n. Okay. So this is kind of laying the upper bounds, as it were, that we know. So now let me tell you what we know in terms of lower bounds. So here's my little table of results for comparing the determinant and the permanent. So the 3 rows here, determinant, the permanent, and gamma is the invariance group, the permutation group we're going to look at. If you just take the trivial group, you're putting no symmetry restriction at all on the circuit, and we know we can get order n cubed circuits for the determinant. We have n squared times 2 to the n, Reiser's formula for the permanent, and lower bounds, super polynomial lower bounds are equivalent to the VP versus VAT question. This sim-n group, by which I mean the action of sim-n, where you apply the same permutation to the rows and the columns, n to the 4th, which is what I just showed you. By the Leverrier's method, I say characteristic 0, but I say, we can get rid of that restriction. And here we have an unconditional exponential lower bound for the permanent, right? There is simply no sub-exponential size circuit that will give you the permanent, at least in characteristic 0, okay? If I relax the notion of my symmetry further, what I call matrix symmetric, in other words, I allow any permutation of the rows and any permutation of the columns, there's nothing to say about the determinant because the determinant is simply not invariant under these full group of symmetries. For the permanent, we can improve the lower bound, not in terms of value, it's still exponential, but we're able to prove this in all fields of all characteristic other than 2. Okay, so it's a stronger lower bound in that sense. And in between, I decided to put in this group because I mentioned it, right, to take the alternating group on both the rows and the columns. We get a lower bound for the permanent, pretty much inherited from here. You have to basically observe that the lower bound there really works with a more restricted group of symmetries. But we also get an exponential lower bound for the determinant, at least in characteristic 0, we have that. So there isn't a polynomial size circuits for the determinant with the full group of symmetries, permutation symmetries of the determinant. Okay. Now, this the table of results, there are really two lower bound constructions in here. And they appeared in two different papers. One was this one, from which we are able to derive that. Okay. And then it's quite a different construction to get this. Okay. But basically we had to develop methods for dealing with this group, and then we noted that basically once we had that, we could improve that one to this. So there's really just there's two fundamental lower bound constructions involved in this set of results. And what I'm going to do for the next, I guess 15 minutes or so, I hope I will try and give you some idea of how this result is proved, this exponential lower bound for the permanent under this, under that group action. One comment to make. I say the lower bounds here are not just on the size of the circuit, but on orbit size. What do I mean? Really what we're proving at each point, for example over here, is not just that the size of the circuit is big. We get that by showing that there is a gate in the circuit whose orbit under the action of this group is of exponential size, and therefore the size of the circuit must be big. And seen this way, you can understand these as lower bound results not about just circuits, or not just about symmetric circuits, but about general circuits as lower bounds on asymmetry rather than on size. What do I mean? Really what this is proving is that in any circuit for computing the permanent, right, with no symmetry restriction, in any circuit for computing the permanent, somewhere along the way there must be a gate which computes a highly asymmetric polynomial. Highly asymmetric meaning that its orbit under the action of this group is of exponential size. Okay, so that's really what we're proving. We're proving you can think of this as not a size lower bound, but as an asymmetry lower bound in the computation of the permanent. Okay, so a little bit of a dive into how we prove this this lower bound for the permanent. Yeah, go on.
Can this perspective allow you to do something for homogeneous groups, like in some meaningful way?
So
SL2 or any other?
I don't have any results on that. I did try to look into this a little bit.
It's worth repeating the question.
Oh, sorry. Yeah, the question was, does this perspective allow you to say anything about continuous group actions, like SL2, for instance? I don't have anything concrete I can say. I mean, I've tried to look into this a little bit. So, okay, maybe worth mentioning, for instance, that there's a work by Landsberg and Risser, I believe, who proved lower bounds on the determinantal complexity of the permanent under what they call equivariant determinantal representations. And that's exactly looking at symmetries under the full, if you will, the continuous symmetry group of the permanent. And we tried to look at theirs to see if there's a translation between back and forth. And we can't see any way you can derive one set of results from the other. And if you want, I can tell you what the obstacles are in each direction, but maybe that might take me a little bit off my pace. So maybe we can do that offline. Okay. So yeah, proof ingredients for this. The first thing is a notion of support. So say you have permutation group delta and subgroup of gamma. And gamma, remember, is a subgroup of sim n here. We say that a set S, subset of n, is a support of delta and gamma if any permutation in gamma which fixes the set S pointwise is in delta. Okay? So the pointwise stabilizer of S in gamma is included in delta. Okay, so in particular, when gamma is the full symmetric group, for instance, sim n, what this means is that delta contains all permutations, which are, if you will, permutations of n outside of S. Right? If fixed S pointwise, any other permutation is included in delta. In the context of a circuit, we say that a set is a support of a gate if it's a support of the stabilizer group of that gate, or if you will, the invariance group of that gate. Okay? This is just introducing terminology. For example, the output gate has empty support in the sense that everything in gamma fixes it. Okay? That was by definition of gamma invariance of the circuit. An input gate labeled by a variable xij, let's say, right? And now I and j are in 1 and n, has support of the two elements at ij in the sense that any permutation, we're assuming there's only one input gate for every variable, any permutation which doesn't move I and j doesn't move this gate. Okay? So, yeah, an input gate has a two-element support. Output gate has empty support. And in general, if you have a small support, you have a large stabilizer group, right? Because everything that moves, that's n minus the size of S factorial permutations all stabilize the gate. Okay, so if it has small support, it has a large stabilizer group and therefore a small orbit. Okay? And the support theorem gives us a sort of converse of this. When you have a small orbit, and therefore a large stabilizer group, you in fact have small support, it turns out. Okay? So, yep.
Back to the support definition.
Yeah.
So then if I have a multiplication gate like xij times xik, what's the support?
It will be ijk, for instance.
It's just ijk.
Yeah.
Okay.
Because that will fix both of those.
What you have?
Yeah, sorry, my question, just to repeat,
Yeah.
I guess, what is the support, like, just another example, like, a product with like xij and xik.
Yep. So you have the product xij, xik, right? Now, any permutation which fixes ij and k fixes this gate, right? Now you're right. There are other permutations which fix the gate as well, but that's why we only ask that the fixing the support is included, right? It's not an exact characterization of the invariance group of this. So there are permutations, for instance, swapping j and k, which will still fix this gate because it will fix this. It fixes this setwise, but that's okay. Ijk is still a support of this gate. What we're looking for is there's a small set of elements such that fixing it will fix the gate, and that means that the stabilizer group of this gate is big when there's a small set of supports, right? Yep, exactly. Okay. So, and there's a converse in the sense that if a gate has a large stabilizer group, which is necessary if it has a small orbit, then it has small support. I'll just say a little bit more about this on the next slide. Which means basically the stabilizer group contains within it a large symmetric group. And so the way what we're ultimately aiming to do is show lower bounds on the support size, right, of gates, which gives us lower bounds then on the orbit size, which is what we're after. And roughly speaking, a super constant support means super polynomial orbit size, and linear size support means exponential orbit size. Okay, that's so we're trying to show that basically any circuit for the permanent must contain gates whose support size is super constant, or in fact even linear, okay, and therefore their orbits are necessarily big. Okay. I say this now. I stated this as a sort of converse to the statement that gates with small support have small orbits. Note, it is not the case that every group with small index has small support. I mean, there's an obvious, right? So not all groups of small index contain a large symmetric group. The obvious counterexample is the alternating group, right? The alternating group has index 2 in the symmetric group, but it doesn't contain within it any large symmetric group, right? You have to fix n minus 1 elements to get a stabilizer group which is contained inside it. But really, turns out this is the only obstacle. Classic theorem from permutation group theory says that if you have a group essentially of polynomial index inside the symmetric group, then it contains within it a large alternating group, right? Not necessarily a large symmetric group, but a large alternating group. So in the context of the circuits, as long as you can rule out the case that the stabilizer group of a gate is in fact an alternating group or contains a large alternating group, then it must contain a large symmetric group. And we can do this by sort of an induction on the structure of the circuit, it turns out. So that gets rid of, and this is why we know that essentially if you have polynomial size orbits, you have constant size supports. Okay. When we want to prove a lower bound for the alternating group as we did for the determinant, then we can just use this directly, right? But okay, I'm not getting into that. So that supports. Now what we want to do, I mean, the support is sort of part of the methodology. We want to construct for a polynomial P, and think here the permanent, a pair of matrices so that they have distinct values for their permanent, but they can't be distinguished by circuits with small support. Okay, that's the way we're going to get our support lower bound. And we're actually going to construct 0-1 matrices, so you can think of them as biadjacency matrices of a bipartite graph. So think of a bipartite graph with parts A and B and an edge relation between A and B. And now the thing is that we're looking at, we're counting the number of perfect matchings in this bipartite graph. That's the permanent, and that's a value that's invariant under an arbitrary permutation of A and an arbitrary permutation of B, which is our sim times sim action on this graph. Okay, so we want to find a pair of graphs, bipartite graphs, with a different number of perfect matchings, but which cannot be distinguished by circuits with small support. And the way we show that they can't be distinguished is by what we call a bijection game. So a bijection game is a two-player game played on a pair of graphs, G and H, with k pairs of pebbles, between two players who we call spoiler and duplicator. Okay? So think of it as spoiler is trying to demonstrate that the two graphs are different. Duplicator is trying to pretend that they're the same. Spoiler is limited in terms of the resources available to it to k pairs of pebbles. And at each move, so the pebbles are placed either on elements of the graph G or elements of the graph H. So in each pair, AI will go on a vertex in G, BI will go on a vertex in H. And at any stage in the game, we have some pebbles on these, some pebbles on those. I want to distinguish notationally between the pebble and the vertex it's placed on. At each move, spoiler picks up a pair of pebbles to move. Duplicator chooses a permutation pi and gamma. Okay, I should have said, it's an initial bijection between the vertices of G and the vertices of H. Duplicator chooses a permutation in gamma, which has the property that for pebbles other than the one that spoiler picked, right, the vertices composing pi with the initial bijection H will map AJ to BJ. Okay, so it keeps, the sort of pebble positions are preserved by, this kind of restricts duplicator to choosing permutations in gamma which fix pointwise the small set of k elements which are currently pebbled. Okay? And then spoiler chooses somewhere to place the pebble AI, and BI goes on its image under this bijection, pi composed with H. If the partial map is not a partial isomorphism of the graphs, in other words, it takes some edge to a non-edge or some non-edge to an edge, spoiler has won, having demonstrated a difference between the graphs, and duplicator wins by playing forever without losing. Okay, that's the two-player game. And the point is, we can show that if duplicator has a winning strategy, then these graphs, seen as matrices, cannot be distinguished by any gamma symmetric circuit with small support. Okay, so the number of pebbles corresponds to roughly the support size. Okay, I'm a bit later than I thought, so I'm going to just run through this very quickly, right? So if you have a gamma symmetric circuit, and you have these two graphs, you think of mapping the circuits to the inputs of the, mapping the vertices of the graph to the inputs of the circuit. By some bijection, vertices go to n. And similarly for this. And if duplicator has the 2k, wins this bijection game, you can show that the circuit will evaluate to the same on alpha g and beta h if duplicator has a winning strategy starting with the initial bijection given by beta inverse alpha. Right? Is this kind of picture clear? I had a picture on it, but I had trouble fitting it on the slide. But anyway, so one way to look at this is if you have a circuit with small supports which distinguishes the two, then the circuit provides a winning strategy for spoiler, right? I think I have this, but basically spoiler places pebbles on the support, start with the output gate, where we know the values are different, which means for some input to that gate, the values are different, and spoiler is going to place pebbles on the support of that gate, and duplicator can keep changing the bijection by permutations in gamma, but we know that permutations in gamma which fix that support don't change the value of that gate. And once the support is pebbled, you then move on to a child of that. And you need, so 2k pebbles suffice because you have k pebbles placed on the support, and you need another k to pebble the support of a child, and then the first k can come off. Okay, that's roughly it. So I won't go over all this. So it remains to get the permanent lower bound, it remains to come up with a pair of bipartite graphs, size linear in K, with a different number of perfect matchings, where duplicator wins the K-pebble bijection game. So size linear in K, that's what's going to give us the exponential lower bound, right? If we got size K squared, we would get a 2 to the square root of n lower bound, for instance. Okay. And as I say, we actually give a construction where the number of perfect matchings differs, in fact, by a power of 2, which means that the value of the permanent is distinct in any field of characteristic other than 2. Okay. So how do we construct this pair of graphs? I mean, this is comes from a sort of a variation of a standard construction known in logic as the CFI construction. You start with a 3 regular graph, and you replace every vertex with a gadget that looks like this. Well, this 5 vertex gadget, and then every edge gets replaced with a pair of vertices. So here you see edges going out the other way. They're basically going to the gadget corresponding to, to the next gadget along in each of the three directions. Right? We have a three regular graph f. Every vertex with three neighbors is being replaced by this gadget, where this is the three edges, and that's replacing the original vertex. The connections are such that we have a central vertex here for each even-sized subset of the three edges, and this VFG is connected to F1, G1, because F and G are in there, but H0 because H is not in there. Okay? And we add one more vertex here, which is neighbor to all of those. That makes the whole thing a four regular graph, and it's four regular bipartite graph, so we know it has perfect matchings, lots of them. Okay? And then, so that's one graph, and the other graph, you basically, in exactly one arbitrarily chosen vertex, you replace the gadget, so instead of even-sized subsets, you're taking odd-sized subsets. Okay? And the point is that this one local difference between the graphs can be hidden by the duplicator in the game, because you can essentially swap an edge to make this difference in this gadget appear in the next gadget along instead, right? And you can follow any path along in the original graph f to hide the twist anywhere. And so we get that as long as the graph f you started with is connected and has tree width at least k, I'll say a bit more about tree width in a moment, then duplicator has a winning strategy in the k-pebble bijection game, played on the two graphs G and H, with the symmetry group I picked, namely arbitrary permutations of the two parts of the bipartite graph. Okay. Tree width, if you're not familiar with it, is a sort of measure of connectivity of a graph. Sometimes that is seeing how tree-like the graph is. Graph has tree width k. Basically, if you can cover it by subgraphs of at most k plus 1 nodes in a sort of tree-like fashion. That's not a definition. That's a rough intuition and a picture to help the intuition. Okay. So that's pretty much it. So we know there are three regular graphs of tree width k and of size linear in k, and so the result follows. Okay. Now, in the sort of 7 or 8 minutes, so I should have said the result follows, because I didn't explain why they have different numbers of perfect matchings, but basically you can show that the two gadgets actually have different number of perfect matchings when you assume that of the two vertices on the three pairs of vertices corresponding to the edges, if you assume one in each pair is paired outside, matched outside the gadget, then the number of matchings inside the gadget is different for the odd and the even gadgets. Okay? And a little bit of counting then allows you to prove that G and H have different number of perfect matchings, and the difference is in fact the power of 2. Okay? So that's pretty much the sketch of the proof of the permanent lower bound. I said in the last few minutes I will tell you a little bit about some newer work. So suppose we have a family of polynomials. I'm indexing it with two numbers now, m and n, because I'm thinking of these as m by n matrices, and m and n I can now vary independently, so not necessarily square matrices. And let's say we're working over the rational field. Okay? And I'm assuming that these polynomials are matrix-symmetric. So permuting the rows and permuting the columns independently doesn't change the polynomial. And we want to know when can we compute these with symmetric circuits, Siemens by Siemens circuits, of polynomial orbit size. Okay, I mean, we're interested in polynomial size, but orbit size is what we can understand better. And it turns out we can actually give a complete characterization now, right? So I'll tell you what it is. It's in terms of homomorphism polynomials. So let me tell you what a homomorphism polynomial is, and then I'll just state the result. So say we have a bipartite graph f, with entries in 0, 1. And let's say we have a matrix M. Sorry, given such a matrix M. Something. I realize. Oh, okay, so M. Think of M as the biadjacency matrix of F. I think is what I'm saying here. So M is the biadjacency matrix of F, and say we have a matrix of variables now M and N, which is different from A and B in general. Okay. Then this homomorphism polynomial is this polynomial here. It's the sum over all maps from A to M and B to N of these monomials, which is x f of I, g of j, taking the product over all values of I and j, for which mij is non-zero. Okay? So if M is the biadjacency matrix, it's just 0, 1. So this is simply the product over all the edges that this maps to. And this is the homomorphism polynomial because if you put in for x an arbitrary bipartite graph, this will evaluate the number of homomorphisms from F to that graph. Right? If you put in for the variables x, you plug in the biadjacency matrix of an arbitrary graph on M times N, this will give you the number of homomorphisms. Okay. And here's the theorem I just wanted to state. This is in joint work, was in ITCS this year with Tim, who's over here, and my postdoc, Benedict Pago. Basically, a family of polynomials computed by is computed by a family of matrix-symmetric circuits. As I said, we'd have a complete characterization with polynomials for orbit size if and only if there is some constant k, so that each polynomial is a linear combination of homomorphism polynomials taken from graphs of tree width at most k. So you know that tree width that came in our lower bound proof is in some sense not accidental. It is inherent to this notion of polynomial orbit size. Okay, so I wanted to conclude there. I mean, there are plenty of open questions here. I mean, I gave you a table of results specifically for the determinant and the permanent, but you can vary the symmetry group, right? And you can ask questions. I mean, I think what the table is showing you is that there's a trade-off between the amount of symmetry and the size of the circuits you want to do. And so there's a lot of variation to explore there. What are the symmetry groups? The methods based on support really work for symmetric and alternating groups, but I think you need other methods for other symmetry groups. There's also space to explore other polynomials other than the determinant and the permanent. So I think there's a lot to do over here. And just, I thought I'd tell you the results pretty much are all that I've presented are all from these 3 papers. Okay, and I'll stop there.
Question here.
Hi, I was just wondering, is there any way of sort of meaningfully defining complexity classes here? Underestimated with preserving reductions or something?
Tim's giving a talk after the break. I think he'll tell you more about this.
So your lower bound techniques extend to circuits where the gates are not just plus and times, but let's say the gates are computing arbitrary symmetric polynomials.
Yeah, I think that's right. I think the only assumption is that each gate is completely symmetric. It's fully symmetric. That's right.
No, I didn't.
freedom for the determinant. Do you have results for that?
You're right. They should. Well, in some sense, we haven't looked closely at that. But I think I mean yes, we should be able to get lower bounds for the determinant. You're right with the depth and symmetry restriction. I don't have an answer.
And also relating to Ben's question, the full symmetric polynomial.
Yeah.
If you allow one gate, then it's trivial. But if you want a symmetric circuit computing it, then it should be larger, right?
So you're saying you're taking that elementary. I see. So you wanted it. So my intuition is the best you can do is the sum of polynomials representation.
There's also Benon's trig. Benon's trig is symmetric.
Right, that it's more than one. No, that's what I mean. It's more than one gate.
I see. Yeah.
I can ask one more question. As the chairman, I can ask a dumb question. In your lower bound proof, you had these two graphs with a permanent that differs by power of 2. I suppose this is the reason why the proof doesn't work in characteristic 2.
That's right.
Is it completely clear that you cannot tweak the proof and make it work in characteristic 2?
Okay. Well, possibly. I mean, so we could try and construct the graph so that the number of perfect matches differs by power of 3, for instance, right? And still play the game. I think that's probably, that might well work. Yes.
Okay. Yeah, the determinant being equal to a permanent in this case is not an obstacle.
It's not an obstacle, I think. Well, so there is a bit of a question. Yeah, no, you're right. Okay, let me just. So, if I go back to my table of results, right? The place where we have a big difference between. Sorry, it's a long way back. So the place where we have this exponential gap is under this symmetry action, but here we only get the permanent lower bound for characteristic 0 in any case. And the way we get that from this, actually simply by looking at the same graph, but looking at its adjacency matrix rather than its bi-adjacency matrix. Okay? And because that's sort of its permanent is the square, the permanent is the square, so the difference between the two permanents here is a power of 2, but we can't really say anything about the difference between their squares, right? And that's why we know it works in characteristic 0, but not. But you're right, here the determinant is pretty much irrelevant, so we might be able to actually get rid of that condition. Yeah. So, that was.
I have a question. So, matrix-symmetric refers to the second column, but it would be sim n, right?
No, this is what I call matrix-symmetric.
Yes. So I was wondering, so you have this lower bound for the permanent, the exponential, and I was wondering how is it now exactly related to the characterization result? You have a characterization that you have such matrix, symmetric, families of symmetric circuits, and there's a characterization in terms of the graph homomorphism, but now I'm wondering, do you use this for proving the lower bound, or is it just an additional insight?
So in some sense, we got the lower bound first. That was an older result. And now we're kind of generalizing this. And so in particular, we know that the permanent cannot be expressed as a linear combination of homomorphism polynomials of bounded treatment. Right? That kind of then follows from the characterization result.
And why do we know that for the permanent?
Well, I mean, that kind of follows from the characterization result, as I said. So we have a lower bound for the permanent.
It's a conclusion.
It's a conclusion, yes.
I see. That's the logic. So it's a conclusion.
Yeah.
Okay, that was my question.
Okay.
Thank you.
Okay. All right.
if things like depth reduction preserve the symmetry. Like for example, if we started off with a symmetric circuit and we did the standard BSBR reduction, at least it seems like it breaks symmetries.
Yeah,
But is the result just false or?
no, I don't know that. No. So wait a minute. I don't know. I don't know what is false, but you're right. You're right. So the method is symmetry breaking. I think it should be. I think it should be possibly just. But okay. I don't want to commit to this. Is it? Yeah. Okay.
In this characterization, you have some translation from, let's say, sim n times sim n to tree width.
That's right. Yeah.
Do you have a general mechanism? You start with a group, a subgroup of this, and get some graph property out of it? Some graph?
No, so the thing is that worked was precisely that for these groups, as I said, once you have the symmetry or the alternating group, we know that when you have polynomial orbit size, so polynomial index subgroups, then it has a small constant size support. And once you have a circuit with small supports, you can get this graph tree decomposition, and then that gives you the tree, that gives you the relation to tree. For other groups, we don't really have this notion of support. So maybe there is something, some more general notion to be recovered there, but we don't.
One last questions, or we can stop here. Thanks again.